In this video, we're going to tackle 3 probability paradoxes: the birthday paradox, the two-child paradox, and the disease test paradox. Now, these 3 are absolute classical problems that everyone gets wrong the first time they see them. In this video, I'm going to show you the mathematical tools you need to calculate the right answer in all 3. But not only that, I want us to see why it works and to understand what makes each problem counterintuitive. The tools that we're going to learn here, conditional probability and probability trees, are like the bedrock of probability theory. As a math professor, I still use these tools and ways of thinking about probability in my research. Now, what exactly are these problems? The birthday problem asks a very simple question. In a room of 23 people, what is the chance that 2 of those people share a birthday? And you might think, okay, there's 365 days in the year. If I fill a calendar with 23 random days out of 365, most of the calendar is empty. So the chance should be very low, right? Wrong. The chance is over 50%. It's 50.7% for 23 people. And we're going to see actually that 23 people is the first number of people where it goes just above 50%. This is way less than you might intuitively think. And we'll see in our explanation why that is. The next paradox is the two-child paradox, which is stated like this. Mr. Smith has 2 kids. Given that at least one of them is a boy, what's the chance that they're both boys? And you might think, okay, you just told me about your first kid. Then the chance of the second kid being a boy should be 50%, right? Wrong. The answer is 33.3%. And the reason I like this paradox, the 33.3, I can get my head around that one. The thing that gets me with this one is it has a sequel, which I call the two-child paradox 2 Tuesday edition. And it says, Mr. Smith has 2 kids. Given that one of them is a boy born on a Tuesday, what is the chance that they're both boys? And now, if you've done the first part of the paradox and you look at the second one, you're thinking, okay, you told me one of the kids is born on Tuesday, but that doesn't matter, so it should still be 33.3% again, right? Wrong. This time, the probability shoots up to 48%. It goes from 33 to 48. This is closer to your intuition of it should be close to 50%. It's not exactly 50%, just a little bit less. What is going on here? Well, we're going to see when we get to it. Last but not least, I have another classic that I call the rare disease paradox. And in this one, we're going to see a situation where there's a medical test for a disease that is 99% accurate. But even if you test positive for it, you still only have less than a 10% chance of actually having the disease. How can that possibly be? So here are the timestamps for the 3 different paradoxes if you want to skip to your favorite. But if you do watch the video in order, you're going to build up the skills of probability trees and then conditional probability that lets you understand each one as they get more and more complicated. In the birthday paradox, we're trying to answer the question, how many people do you need to have in a room before it's likely that 2 people have the exact same birthday? And to make this quantitative, we're going to imagine there's exactly 23 people in the room, and we're going to find the probability of a birthday match somewhere amongst those 23 people. To do this, we're going to need to make an assumption, which is that every single day of the year is equally likely to be their birthday. So every single day has a 1 out of 365 chance of being their birthday. January 1st has the same probability as July 1st. They're all equally likely. We're also going to assume that people's birthdays are independent. So if you know person 1's birthday, it doesn't give you any extra information about what person 2's birthday is, and so on. Now, of course, this is not exactly realistic to real life. Some parts of the year have more babies than other parts of the year. But it's an interesting problem already with this simple assumption. And the interesting thing you can do once you've solved it is you can compare to real life and see how different is it. Now, even with this very simple assumption, the problem is already quite hard. What makes it hard is that even though people's birthdays are independent, so like knowing exactly person 1's birthday and knowing exactly person 2's birthday, those are independent, can be calculated separately. The types of questions we're going to ask about birthday matches, those are dependent. So for example, if you look at person number 23 in the blue hat standing way over there, and you ask a very simple question like, what is the probability that person number 23 has a birthday match with somebody else in the room? The answer is, it depends. If you take persons 1 through 22, and you write all their birthdays on a calendar, they could have 22 different birthdays, or they could all have the same birthday. And when person number 23 walks into the room, the chance that person number 23 is going to have a birthday match with somebody depends on how many different unique birthdays persons 1 through 22 have on the calendar. And this kind of dependence is what makes the problem hard. To get around this, we're going to use the idea of a probability tree. And a probability tree essentially lets you make if-then statements about things that may or may not happen. And we're going to have statements that are like, if persons 1 through 22 all have different birthdays, then when person 23 walks in, the chance of him having a birthday match is 22 out of 365. So a probability tree is going to let us take these if-then statements and turn them into rigorous mathematics and actually find the probability. To do this, I'm going to take person 1, I'm going to put them in the room all by themselves, and I'm going to have people enter the room one by one, and we'll kind of build up this probability tree little by little as people enter the room. When person number 2 comes to the door and then walks in, very simple thing, there's only 2 things that can happen. Either person number 2 has a birthday match with person number 1, that has a chance of 1 out of 365 of happening. The reason it's 1 out of 365, again, is because you can imagine a calendar with all the days of the year. Person 1, his birthday is somewhere on the calendar. You put a big stamp where person 1 is. And then when person 2 walks in, their birthday is one of the days chosen completely at random, independent of person 1. And that means there's one target where they would have a birthday match. That's where the stamp for person 1's birthday is. And there's 364 out of 365 days where they would have no match and everybody would have different birthdays. Very simple with person 2 walking in. Things get interesting when we want to ask about person 3. So once again, the thing that makes this problem hard is that if you ask a question like, what is the probability that person 3 has a birthday match with somebody else in the room? The answer is, it depends. It depends on what happened in the tree. In the left branch, person number 2 and person number 1 have the same birthday. So there's only one day on the calendar that person 3 is aiming for. But on the right branch, there are 2 separate days. There's one day where person 1's birthday is, and there's one day, the different day, where person 2's birthday is. And that's what makes this problem hard. Fortunately for us, we only need to calculate the probability that there is a birthday match somewhere. And that means in the left branch, we're actually done. We're finished. We know, because person number 2 and person number 1 share a birthday in the left branch of the tree, that there's going to be a birthday match amongst the 23 people. So we only have to continue calculating what's going to happen in the right branch of the tree. And in the right branch of the tree, we already know that person number 1 and person number 2 have 2 distinct birthdays. And this means that when person 3 walks in the room, the chance that we can write on our probability tree of having person number 3 being the first person with a birthday match is 2 out of 365. This is the beauty of a probability tree. You can break down these dependence questions using kind of if-then arguments. These if-then statements in probability are called conditional probability. This 2 out of 365 is actually a conditional probability. It's the conditional probability that person 3 has the first birthday match given person number 1 and person number 2 have different birthdays. That's what the notation up there means. And there's this really funny notation in probability of a big line here that you would read out loud as given. Given. And by drawing it on the tree this way, we see that it is happening because this branch comes off of the situation. This whole node over here represents the situation where person 1 and person 2 have different birthdays. So that's the beauty of a probability tree, is we can build in these if-then statements and just calculate simple things that we want to calculate. All right, that's the chance of them having a birthday match. Person 3 birthday matches with either person 1 or 2. And of course, the other thing that can happen is that person number 3 does not have a birthday match with person numbers 1 or 2. And then they all have different birthdays. This happens with chance 363 out of 365. Already, with just 3 people in the room, by making this nice probability tree, we can calculate some interesting things. And to do that, we have to use the probability multiplication rule for probability trees. And this says to get an actual probability from a probability tree, you have to multiply along the branches of the probability tree. So for example, in this situation, if we want to know the probability that all these 3 people, persons number 3, 2, and 1, all have different birthdays, that is this little leaf over right here, we have to multiply down the branches. We have to multiply this one, 364 over 365, times this one, which is 363 over 365. In probability class, the way they write this equation down is like this. They say the probability of 2 things happening, of some event A and some event B, is first A has to happen, probability of A, times the probability of B given A. So this is the multiplication rule for the multiplying along the branches, written in a more symbolic way. I like the picture way because I love pictures of multiplying along the branches of the probability tree. Okay, another question you might ask is, what's the probability of a match? And to do that, we can use the sum rule for probability trees. The probability sum rule says you add probabilities of disjoint events. So if you want to know something like what's the chance that the first match was person number 2 or the first match was person number 3, that would be the chance of any birthday match after 3 people, you can add up the probabilities. So in this situation, you can take 1 out of 365. That's the first thing we're going to add. And the second thing we're going to add, we have to do the multiplication rule, 364 out of 365 times 2 out of 365. So the second thing is a product because it is 2 layers down into the tree. And by adding these 2 numbers, because the things are disjoint, that means they both can't happen at the same time, we can just add the probabilities to find the answer. So you can see already, this is the seed of the reason the birthday paradox is a birthday paradox. You might think with 3 people, you have sort of 2 chances of having a birthday match, But actually, there were 3 chances. You see, there was a 1 out of 365 and a 2 out of 365. We're sort of doing a 1 plus 2. That's why things kind of ramp up faster than most people expect. Of course, it's not exactly that because there's this factor of 364 out of 365. Last but not least, there's probably a few people screaming at their screens right now, hey man, you're doing this the hard way. There's an easier way to do it. And the easier way is to use one more fact about probability trees, and that's to use the total probability rule. The total probability rule says when you have a probability tree, the sum of every single different thing that can happen, that has to add up to 100%. In this situation, we have 3 things that can happen. Either person 2 was the first match, or person 3 was the first match, or they had all different birthdays. And that means the sum of these 3 things has to add up to 100%. And this often makes it easier to calculate certain things. So for example, I was calculating what is this one plus this one, which was kind of annoying. I had to go down this branch, I had to go like this. I could have just said, listen, I want to calculate everything except for the all different birthdays. Because everything adds up to 100%, I can just take all different birthdays and do 100% minus that. In our situation, this means the probability for any birthday match after 3 people, you can rewrite it as 1 minus the probability of all different birthdays, like this. So that makes things a little bit easier, and as the tree gets bigger and bigger, this formula is going to become more and more helpful. Okay, we've analyzed to death what happens with 3 people in the room. Let's have another person walk in the room, and let's see what happens. You might be able to spot the pattern already. So person number 4 is going to come to the door. Person number 4 walks in. Again, we don't need to update anything on the left-hand side of the tree. When there was a match with person number 2 or person number 3, we're done. We know that there is a birthday match somewhere amongst the 23 people. We only have to keep analyzing what happens if there is no birthday match among persons 1, 2, and 3. In that situation, we can again use conditional probabilities. So when there is no birthday match amongst persons 1, 2, and 3, then when person 4 enters, we have this nice conditional probability 3 out of 365 that we can draw on our probability tree. And so now that we've added this layer for person number 4, we can easily calculate what's the probability there's a birthday match amongst 4 people. We just update our formula by adding a 4th factor. So now the chance of having all different birthdays is 3 layers down in the tree. We have to multiply these 3 numbers, 364, 363, 362, to get the probability that they have all different birthdays. And then the probability there's some birthday match is 100% minus that. You could also add it up over all these other things. That would be equally good. It would have something to do with 1 plus 2 plus 3, but it's easier to get the exact answer this way. So now that we've done it with 4 people and we've got a nice formula that is very compact, you can probably see the pattern and guess what's going to happen as more and more people enter it. In mathematics, we use this ... to do the heavy lifting of let's do something over and over again. And as we have more people enter the room, the left-hand side of the tree is going to stay exactly the same, only the right-hand side of the tree kind of grows on this kind of event that everybody has all different birthdays. And it's going to culminate in the 23rd person entering the room, way down 23 layers down in the tree, that ... hiding layers 5 through 22. And we're going to have this conditional probability that I talked about in the introduction, 22 over 365. That's the conditional probability that person number 23 has a birthday match with somebody amongst the first 22 people, but only on the event that persons 1 through 22 all have different birthdays. This is the power of the probability tree. Analyzing what happens with person number 23 is hard, except for it's very easy in this specific event where we know already that the first 22 people have all different birthdays. And when the first 22 people have all different birthdays, we know the conditional probability is 22 out of 365, so it fits in very nicely into our probability tree. We can calculate the probability that there's a birthday match somewhere by using the 100% minus rule, 100% minus the chance there's all different birthdays, and we get this nice formula that has a really big product to multiplying all the way from 364 down to 343. There should be 22 terms in this product because there are 22 layers of the tree. The reason it's 22 is because we started with person number 2. Person number 1, when they were in the room on their own, they didn't contribute to our probability tree. And if you multiply all this out, you're going to get a very nice, simple answer. The big product is 49.27%, so it's 0.49. 1 minus that, or 100% minus that, is 50.73%. And that is the final answer. The chance that there is a birthday match in a room full of 23 people is 50.73%. It is just above 50%. So it's more likely than not that in a room of 23 people that somebody will have a birthday match. This is called a paradox because it's so surprising. You kind of think of needing like hundreds of people in the room because there's hundreds of days in the year. The reason your intuition is wrong is you kind of miss this building idea. My little pet explanation for what's going on here is that you should think of the chances as growing quadratically in the number of people. What do I mean by that? Well, when person number 2 enters, there's a 1 out of 365 chance over here. But when person number 3 enters, there's a 2 out of 365 chance. Then a 3 out of 365 chance. So every time a person enters, the chances go up and up. And we're adding all those things. So you end up with something like 1 plus 2 plus 3 plus ... plus 22, which is quadratic in the number of people. So this is approximately 22 squared. And that is the thing that is counterintuitive about the birthday paradox. The chances sort of grow quadratically in the number of people rather than linearly in the number of people. Of course, everything I said is not exactly true because you have to also include the branches along here. So if you want to write it out exactly, it's easier to just use this formula. But you can analyze not just the probability of a birthday match amongst 23 people, but you can say how many people would it take? And I've written a Python script that does just that. Let's take a look at that. So here's the Python script that tests out everything we calculated with that probability tree. The calculation that we made is what I call theoretical probability. That is the calculation, the 1 minus the big product that we had before. And it was a product over n minus 1 terms, where n is the number of people in the room. So this is the probability to have a birthday match somewhere inside the first n people. Of course, as you have more people, the probability of a birthday match can only increase, which we see over here. So this probability goes up and up and up, and we calculated the value when n equals 23. So in the video, we did 20, 21, 22, 23. We calculated this value, which you can see is barely just above 50%. That is what we calculated. The formula in pink tells you what it is for any number of people, and you can see for just 1 or 2 people, very unlikely to have a birthday match. Once you get to like 50 people, very likely you will have a birthday match. You might wonder, okay, if pink is the theoretical thing we just calculated, what is this thing in blue? And I did some what are called Monte Carlo simulations. So this Python script, it just simulates people walking into a room and having birthdays and seeing how many people do you actually need. So if you're into that, there's a link in the description. You can check it out. It's in Google Colab. You can also do what I hinted at earlier, which is instead of looking at the cumulative probability that's always going up, you can ask what is the probability that the nth person is the first birthday match? And those were all the branches on the left side of the tree. The first person 2 is the first match, person 3 is the first match, and so on. You can calculate those. And if you do that, you get this other plot, which I call the probability that the nth person is the first match. And you can see that this probability is going up for a while and then going down. And that's because, as we saw on the branches, the number on the very left branch is going up. It's 1 out of 365, then 2 out of 365, and so on, all the way up to 22 out of 365. They're going up and up and up. But the big spine of the tree is multiplying all these numbers that are less than 1, and eventually that dominates and the numbers start to go down again. So for a while, this is sort of going up linearly, like 1, 2, 3, 4. But because of the multiplication along the spine there, things start to go down. And it reaches a maximum, then interestingly, it reaches a maximum at n equals 20. N equals 20. So the 20th person to walk in a room is the person who is the most likely to have the first birthday match with somebody else in that room. They have an approximately 3% chance to have the first birthday match. This idea of looking at the cumulative probability or looking at the individual probabilities, you can then ask what is the mean, median, and mode, which I did over here in this little code snippet at the bottom. How many people need to enter a room before there is a birthday match? Well, the median is 23. 23 is the first number of people where it crosses 50%. For 23 people, it's more than 50% likely. For 22 people, it is less than 50% likely. The mode is 20. The 20th person is the most likely person to have the first birthday match. And you can do another calculation to find the mean is 24.6166. So it takes approximately 25 people on average to enter a room before there is a birthday match. The reason the mean is a little bit higher than the median or the mode here, you can see from the picture, and that is because you can see the distribution is a little bit skewed. So it has this kind of long tail of unlikely values, but that lead all the way out to, up to 365, where there's guaranteed to be a birthday match. And that long tail is pulling up the mean. So even though the median and the mode are like 20 and 23, the mean is a little bit higher at around 25. And that is the birthday paradox. The next probability paradox we're going to look at is what I call the rare disease testing paradox. Here's the setup. A rare disease affects 1 in 1,001 people. The test for the disease is always positive if you have it, but is only 99% accurate if you don't. Given that you have received a positive test, you went to the doctor, they did the test came back positive, what is the chance you actually have the disease? And when people see this, they think, oh, it's a 99% accurate test. If you test positive for it, it must be like very accurate, probably a 99% chance you have the test. But we're gonna see that the chance is not 99%, but is only 9.1%. 1%. And we're going to see exactly why that is. So it's a much, much lower than what you would imagine. And the reason, the thing creating this paradox is the 1 in 1,001 people. So because the disease is so rare, that is going to affect the chance of actually having the disease even after you've tested positive. Let's see how this works. So to start with, we're going to draw the probability tree. For the first layer of our probability tree, we're going to ask the question, do you actually have the disease or not? And based on the information given in the question, there is a 1 in 1,001 chance you have the disease and a 1,000 in 1,001 chance you don't have the disease. And then based on whether or not you have the disease, then the next layer of our probability tree, we're going to ask for what were the test results. And this again is the magic of the probability tree. We can put in different probabilities depending on whether or not you have the disease. This lets us put in conditional probabilities. And in this particular problem, the conditional probabilities are given to us. They told us you are always positive if you have the disease. So it's going to be a 100% chance to test positive if you have the disease. But it's only a 99% chance to be accurate if you don't have the disease. So that lets us do two different things in the two different branches of the tree. Let's see what the next layer looks like. So if you have the disease, there's a 100% chance you will test positive. If you don't have the disease, there is only a 1% chance you will get a positive test, and there's a 99% chance you will get a negative test. So that's what 99% accurate means here. It's going to have the correct result 99% of the time. So this probability tree perfectly represents the situation given, and we can use it to calculate what we want. Before we do that though, I'm going to represent the same exact information in the probability tree in a slightly different way that I think is a little bit more intuitive, and it's going to help you understand what is going on in this probability tree. And that way is to imagine a population of 1,001 people. So imagine there's 1,001 people that are sort of representing this hypothetical scenario that we're talking about. Of these 1,001 people, we said 1 out of 1,001 people on average has the disease. So we can kind of imagine that there's one person over here who has the disease, and there's 1,000 people in the population who definitely don't have the disease. And then we can further subdivide, just like we did in the probability tree, this population of 1,001 people, they will go and imagine they all get tested. What's going to happen is the person with the disease will test positive, and then we're going to have 10 people out of our population of 1,000 who also test positive. And that's because the test returns the wrong answer 1% of the time. So even though this population of 1,000 people here in orange, none of them actually have the disease, when they go and they take their test, 1% of them are going to come back with a wrong answer, a positive test result. So there's 10 people over here, 1% times 1,000, that have the wrong test result. They are positive even though they don't have a disease. These are called false positive sometimes. There's also 990 people standing over there in the red hats. They are people who don't have the disease and also had the correct test result that it came back negative. And what I want to emphasize is that this probability tree and this population of people are two identical ways of looking at the problem. A probability tree is a nice representation of subdividing the probability space, the space of all possible things that could happen. It is being subdivided into different events based on these branches and if-then statements. If you have a population of people, you can also imagine each person represents an element of the probability space, and you're subdividing them into groups. The probability tree at the end of the day has 3 groups. The population of people at the end of the day has 3 groups. They are showing the exact same idea in 2 different ways. The nice thing about with a population of people is that it's a little bit easier to intuit what things mean. When someone says, given that you've tested positive, okay, that means you're somebody wearing the green hat. Given that you've tested positive, you're one of these 11 people. What is the chance you actually have the disease? Well, there's 11 people in green hats, and only one of them actually has the disease. 10 of them were these false positives. So what's the chance you actually have the disease? It should be 1 out of 11, right? Well, let's calculate it properly, and we're going to get the same answer 1 out of 11 that you would do kind of the intuitive way. And to do this, we're going to use the rule for conditional probabilities in trees, which I call the conditioning rule. And I stated it like this: you cut away the impossible and then renormalize what's left. And it is nice that this is a tree, because pruning a tree is when you take a big set of scissors and you cut off pieces of the tree. That's exactly what we're going to do. We're going to cut away the impossible first. So in this situation, because somebody told us, look, you tested positive, that means any situation where you didn't test positive, that is impossible. So this one over here, where we tested negative, that is impossible. Let's cross that out with a big X. There's the big X cutting off that big part of the tree. Or equally well, if you want to think about it as the population of people, we are saying, look, there was this population of 1,001 people. We are not one of the 990 people over there. That did not happen to us. So that's the first part of the conditioning rule. You cut away the impossible. The next part of the conditioning rule says renormalize, a really nice buzzword from physics, renormalize what's left. Renormalize means make sure you think of everything else that can happen as adding up to 100%. If you remember from the birthday paradox, we said one of the rules for probability trees is they always have to add up to 100%. Well, in my new tree, right, I started out with this very nice tree over here that had 3 possible things that could happen, and I cut one of them away. Well, if I cut one of them away, it no longer adds up to 100%. It adds up to less than 100% because there's only 2 possible things that can happen. Renormalize what's left means just boost up all the probabilities, multiply them by whatever you need to, so that the total value of the tree adds up to 100% again, like it is supposed to. You'll see what this means for the population. It's very simple. Instead of thinking of this being out of 1,001 people, we're going to think of it as being out of 11 people. As we do the calculation, you'll see how this comes out. So if we now go to calculate, and what we're calculating in this problem is the conditional probability. What is the probability you have the disease given that you tested positive? Well, to start with, the probability is given by the multiplication rule. So multiplying down the branches of the tree, we have 1 out of 1,001 times 100% coming from the first branch and then the second branch. That's the only way you can have the disease and test positive. That's the only thing that can happen, just that one branch of the tree. And so it's the product of those 2 things. Now, if this was a regular calculation, that would be it. We'd be done. We'd have the answer. But this is a conditional calculation. So the thing we have to do is we have to renormalize. We have to make sure that we're somehow only accounting for those 2 things. We want the whole probability tree with just these 2 things and this guy cut out to add up to 100%. And the easiest way to do that is to think of it as out of whatever the sum of these 2 things is. So we're going to divide by this sum over here. And the sum is the sum of all the possible things that could happen in our restricted tree. So it's the sum of this branch going down here and this branch going over here. And by dividing it by everything that can happen in the tree, we are sure that we're sort of counting for the whole tree as being 100%. This is a little bit like if you have 7 things and someone says, what fraction of the things were these 2? And we say, well, okay, there's 2 out of the total of 7. So that's what we're doing. We're saying the thing we want versus divided by all the possible things that we could have. And in this situation, all the possible things isn't 100%. It's something less than 100% because of the conditioning. Like I said before, in the population, this was all very intuitive. We had a population of 1,001 people. And instead of dividing it by 1,001 and saying the chance of having the disease is 1 out of 1,001, well, now we're down to 11 people. So the chance should be 1 out of 11. And that's exactly what this calculation is doing. Look, let's simplify it a bit. It's going to be 1 out of 11. So if we simplify out those 1,001s and those go away, we have 1 times 100% on the top. That represents this one guy over here. And on the bottom, we have 1 times 100%, this guy again, but then 1,000 people times 1%. Those are exactly these false positives over here. And if we now simplify, this is 1 divided by 1 plus 10, also known as 1 over 11, like we intuited, which is approximately 9%. Now, this probability paradox, it has real life implications. This is the reason when you go to the doctor, they don't just give you every possible test under the sun. If they were to give tests to everybody for everything, there would just be so many false positives that it would really overwhelm the true positives and it would actually make things harder to do. This is why the doctor asks you a bunch of questions like, do you have symptoms of this? Do you have symptoms of that? Do you have a family history of this disease? This increases the rate of the rare disease. So something that might be a 1 out of 1,001 in a population, if you are showing symptoms of it and you have a family history of it, maybe now it's only 1 out of 10. And so by reducing the rarity of the disease, we can make the test more accurate to return useful information. I will also say you can also equally well calculate everything I've done here using the so-called Bayes rule, which is a great rule. There's a Veritasium video exactly on this problem using Bayes rule. To me, what we just did is the reason Bayes rule is the way it is. We've sort of derived Bayes rule. I haven't actually said what Bayes rule is, so if you want to know what that is, please go watch that video instead. The last paradox we're going to look at is called the 2-child paradox, and it goes like this. Mr. Smith has 2 kids. Given that at least one of them is a boy, what is the chance that they are both boys? And to answer this, we're going to have to make an assumption, which is we're going to assume the simplest possible thing, that children are born 50-50 boy or girl independently at random. Just like in the birthday paradox, this is not actually true to real life at all, but it is already an interesting problem. Actually, sometimes people state this paradox with coin flips instead, because we're basically treating each child as a coin flip, 50% boy, 50% girl. Not true to real life, but interesting math nonetheless. And if you make this assumption, you might have the intuition that, okay, you're giving that one of them is a boy. Well, the other one is just an independent coin flip. It should be 50-50, right? So you might think, question, is the answer 50%? No, that's what makes it a paradox. The answer is 1/3, also known as 33%. So we will show that that's the answer to the paradox. And the reason it's 1/3 is kind of there's 2 ways that it can go boy-girl. It can either go boy-girl or girl-boy, and you will see exactly what that means in the probability tree. So if we draw the probability tree for this situation, we're just going to do it by the first child and the second child. The first child is either a boy or a girl. We're assuming it's 50% for each. And then the second child is also either boy or girl in both situations. Now again, you can do this totally through the probability tree, but there is another nicer way to represent it in this situation, which is to use a grid. And the reason the grid works so well is because the first child and the second child are independent. So regardless of what the first child is, what's going on in that second layer splits up the same way. So if we draw a grid, it will look like this. The rows and the columns are both identical. So the rows represent the first child, either boy or girl, and the columns represent the second child, also either boy or girl. And because the things are independent, that is why everything sort of multiplies. All the lines are straight. Regardless of your x coordinate, your y coordinate is doing the same kind of thing in both situations. So we end up with this nice grid with 4 possibilities: boy, 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 girl, girl, boy, or girl, girl. Now to solve the problem, we can either do it on the probability tree or on the grid. We're going to use the same conditioning rule we learned in the rare disease paradox. We're going to cut away the impossible. In this situation, we are given that one of Mr. Smith's kids is a boy, so we can cut away the situation of girl, girl. We are not in the universe where Mr. Smith's children are girl, girl. We were told that that's impossible. Let's cut it out of our tree. And if you do that, you cut away girl, girl. On the grid, it would look like cutting away the bottom right corner. Now there are 3 things left. There are boy, 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 or boy, girl. According to the rule for conditional probabilities, all 3 of these things, we should calculate the probabilities the way we were doing it before by multiplying. So they're all going to be equally likely. And the only thing we have to do differently is we have to make sure when we renormalize, we divide by the right thing to make it sum up to 1. So that calculation will look like this. The conditional probability that Mr. Smith has 2 boys, boy, boy, given at least one is a boy. So it's going to look like this. Here's the proper calculation from the probability tree. The numerator is the multiplication rule, 50% times 50%. That's the boy, boy category. And the denominator, I have summed up all 3 things that can happen in the probability tree after we have cut away girl, girl. So the 3 things that can happen are boy, boy, 1/2 times 1/2, girl, boy, 1/2 times 1/2, or boy, girl, also 1/2 times 1/2. That is the proper calculation using the conditioning probability rule. Things we want, boy, boy, divided by all the things that are left in the probability tree. It is easier to see in the grid. In the grid, it looks like, okay, we got 3 squares. Boy, boy is the top square over here, and girl, boy, and boy, girl are the other 2 squares. In fact, each of these squares, if you sort of think of the width of these things as being 1/2, 1/2, each of these squares is area 1/4, 1/2 times 1/2. So if you think of area here as representing probability, then this is exactly doing that calculation over there. And of course, it simplifies. If you have 1 square out of 3 squares, the answer has got to be 1 out of 3 equals 1/3. That is the answer to the original version of the 2-child paradox. But the reason I like the 2-child paradox so much is that it has a sequel, the 2-child 2-Tuesday paradox, which says that Mr. Smith has 2 kids. Given that at least one of them is a boy born on Tuesday, what is the chance they are both boys? And at first you say, okay, this being born on Tuesday has absolutely nothing to do with anything going on here. So of course the answer should still be 1/3, like we just calculated, right? But the answer is no, it's not 1/3 anymore. Now the probability has jumped all the way up to, the answer is something like 48%. What on earth is going on? Why would the probability change when you're given that he is born on Tuesday? It is a very subtle thing, and I think we can see it if we do the probability grid and the probability tree for this updated problem. So the first thing we're going to do is we're going to change our probability tree. Instead of doing boy and girl, we're going to have 3 categories of things that can happen. There's either boy born on Tuesday, boy born on not Tuesday, or girl. So instead of having 2 possible things in each level, we're going to have 3 possible things in each level. What does that look like? It looks like this. So our probability tree is splitting up into 3. I have assumed that being born on a Tuesday has a 1 out of 7 chance of happening, and being born on a not Tuesday has a 6 out of 7 chance of happening. And I've also assumed it's got nothing to do with whether or not you're a boy or a girl. So independently at random, that's why I get 1/7 times 50% and 6/7 times 50% for those 2 types of branches. You'll notice here I still have 2 levels on the tree for the first child and the second child. You could equally well set it up with being born on Tuesday or not as a separate level. So when you make a probability tree, it is up to you how you want to set it up. You should set it up in a way that is convenient for what you want to do, and this one is convenient for what I want to do. So I have it set up with 2 levels with these 3 categories: boy born on Tuesday, boy born on not Tuesday, and girl. So we've subdivided boy into 2 kind of different types of boys, the Tuesday boys and the not Tuesday boys. If you do that on the grid, then what it's going to look like is this girl square is not going to change at all, but the boy is going to get divided up into 2. So it's going to be kind of like split into 2 parts, the boy Tuesdays and the boy not Tuesdays. Let's see what that looks like. So now it looks like this. So the girl the girls are still on the bottom row, and the rightmost column are still 50% of the each row and column, but now boy has been subdivided into boy Tuesday and boy not Tuesday. I have tried to represent the fact that boy not Tuesday is more likely than boy Tuesday by making it a little bit wider. And once again, if you do this correctly, the areas in this shape should represent the actual probabilities of every single thing. You see, the probability multiplication rule is the width times height rule for areas. So areas become probabilities if you have this nice setup like we do here. And now we have 9 possible things that can happen. We have 9 branches over here, or 9 little boxes over here, all of which are different sizes now. But now we can answer the question which we originally wanted, which is what is the chance that it is both boys? And the thing that makes this a little bit harder is when we're doing our conditioning rule, when we have to cut away the things, we have to cut away all the situations where Mr. Smith does not have a boy born on Tuesday. You see, we were told Mr. Smith has a boy born on a Tuesday. So we have to cut away everything where there is no boy born on Tuesday. What does that look like? So if you do it on the probability tree, it's a little bit annoying. I'll just show you the final answer. So girl, 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 boy, not Tuesday, boy, not Tuesday, girl, boy, not Tuesday, boy, not Tuesday. Those all go away. How did I come up with that? You have to think about it for a while. But if you do it on the grid, it's actually very simple. And that's because you kind of recognize boy Tuesday is can either be this really thin column on the left, or it can be this really thin row on the top. So because we definitely have a boy Tuesday, we're definitely somewhere in this top here. And so when we cut away everything that's impossible, it's kind of easy to see what it is. So here are those same exact nodes I cut away from the probability tree. I'll cut them away from the grid. It's just 2 different ways of representing the exact same idea. So cutting away those 4 things, and now it looks a lot more intuitive. We're cutting around of this big square that is not the very thin row or the very thin column. So finally, we're ready to do our calculation. We're going to calculate the chance that Mr. Smith has 2 boys. But once again, you have to recognize what does it mean to have 2 boys? And actually now there is more than one way, because of our subdivision, that he can have 2 boys. The 3 ways that Mr. Smith can have 2 boys are represented here, here, and here. So these 3, which again, a little bit tricky to see on the probability tree, but very easy to see on the probability grid. They are just the 3 events in the sort of corner, right? So they're the 3 pieces that were left over in the top corner that are also on the most narrow left, or the very tippy top row. And that's where there's 2 boys, but also there's at least 1 boy Tuesday. So kind of easy to see over here, a little bit harder to see over here, but it's exactly the same information. You could equally well work it out this way. To be honest with you, the way I work it out, if somebody gives me the probability tree, is I draw the grid and then I figure it out and then I copy the results over to the tree. There are 2 equally good ways of doing the problem mathematically, but sometimes one is more intuitive than the other. Okay, now that we've recognized what is our conditional tree, we've cut away the things that we don't want, we have identified the things that we do want, we can just divide them, and that will be the probability that we want. So what is the final answer? It's going to be a big calculation. The probability Mr. Smith has a boy, given at least one is a boy born on a Tuesday, it is the division of a bunch of things. The top is a sum of 3 things. Those are the 3 ways that he can have 2 boys, with one of them being born on Tuesday, represented by this little corner over here, divided by the same sum of those 3 things, plus these other 2 things. Let me use this other green color for these other 2 things, and those represent the girl boy Tuesday situations on the top edge and the bottom side over here. Or if you want, they're the 2 nodes on our probability tree corresponding to these other situations where there is a boy born on Tuesday, but the other person was a girl. And you can see them visually over here on the top and bottom. Now, if you simplify this by multiplying through by 7s and so on, you'll get a nice answer, which is 13 divided by the same 13 plus another 14. And again, you can work it all out with the math. It is 13 divided by 13 plus 14, but I want to show you that you can actually calculate that quite quickly from this picture. And that's because you can sort of think of this girl width over here as 7 parts, and this girl width down here is 7 parts, and the boy not Tuesday is 6 parts, while the boy Tuesday is 1 part. And that's because of this ratio that we had of boy Tuesday to not boy Tuesday is a 1 over 7 chance of being born on a Tuesday and a 6 out of 7 chance of being born on not Tuesday. So if you think of the proportions as being this 1 to 6 proportions, then this is going to be area 1, this is going to be area 6, this is going to be area 6, this is going to be 7, and this is going to be 7. So what are the things? Well, on the top, it's a 1 plus 6 plus 6, 13. And on the bottom, it's a 1 plus 6 plus 6 again, but now also plus 7, also known as 14. So that's why it's 13 divided by 13 plus 14, illustrated with a picture. If you don't like pictures, just calculate it the old-fashioned way, crunch the numbers. In any case, however you do it, you're going to get the answer of 13 over 27, which is also known as 48.1%. So in this updated Mr. Smith paradox. When you know that one of the children is born on a Tuesday, the probability that the other person is a boy has shot up from 33% all the way up to 48%. What the hell? How is this? Why would the probability change when you're told that they are born on a Tuesday? Well, let me show you mathematically what's going on here. You can kind of think about how big is that square in the corner. And really it is like, if you look at the ratio of this yellow rectangle to the girl rectangle right next to it, those are both equally sized. And the yellow rectangle over here and the girl rectangle down there, those are also both equally sized. So the reason it's less than 50% is exactly due to the overlap, the area of the combination of boy Tuesday, boy Tuesday. So the rarer of the type of thing that Mr. Smith tells us, if he says, I have two boys and one of my boys was born under the full moon as the Gemini was in Saturn and Taurus was in blah, whatever. If he tells us some super rare thing, the chances that he would have two boys that were both born under these very specific circumstances is extremely small. And so the area of this overlap gets really, really small. And the probability that the other child is also a boy gets closer and closer to 50%. Another way you can intuit it is if when you say very, very specific things about one of Mr. Smith's children, it sort of narrows down who that child is exactly or closer to exactly. And then once we know the identity of one of the children, well, then the other child is like literally just a coin flip. Like imagine I told you Mr. Smith has two children and one of them is this guy. What's the probability that his other child is a boy? Well, we'll just wait till Mr. Smith has the other child and then it'll be 50%. So if you know the exact identity of one of the children, it's exactly 50%. And sort of the vaguer information you give about Mr. Smith's child, the larger you make this area, and then the closer and closer it gets to 1/3. So it's always going to be between 1/3 and a half, where very specific things are close to a half and very vague things about his other boy go all the way down to 1/3, like we did in the first side of the paradox. And if you like this visual way of thinking about the probabilities instead of the probability tree, then there's a really excellent 3 blue 1 brown video where he does Bayes' theorem using this kind of thing. Actually, if you're at the end of this video and you're like, hey, this was great, I want to learn more, you should really learn Bayes' theorem. So either go check out that Vertasium video that I mentioned earlier or the 3 blue 1 brown video. It's a really great next step where you see how you can take these rules for conditional probability and package them into this like really simple to think about way, which is Bayes' theorem and the sort of Bayesian way of thinking about things. Okay, that's it.